Hello and welcome back to the exciting world of structural engineering analysis. Today we're going to continue looking at reactions, but this time we're going to look at a different type of load, a distributed load. This is a load that occurs across a distance. To start off, we're going to look at one that is uniformly distributed and is on a simply supported beam. Let's get to it. So to start off, as I said, we're going to look at a simply supported beam, which you can see here, with a uniformly distributed load. That means it's a constant 10 kilonewtons per meter in this case. The first thing that I want to do is to draw a free body diagram. I can see that at point A, I've got a roller support. So I'm going to replace that support with a single load, AY. And at B, I've got a pin support, which means I need to replace it with two perpendicular reaction forces, so By and Bx. Since this is in 2D, it means that I can use three equations of equilibrium: sum of forces in x, sum of forces in y, and a moment. We're going to start off with the sum of forces in x equals 0, with this being my positive direction. So in x, I've got Bx, and that is it. There are no forces or other reactions in that direction, so Bx equals 0. I can now continue to the sum of forces in y equals 0, with this being my positive direction. And this means that there is equilibrium in y. That is, the forces are balancing each other out. So in this case, I've got ay plus by going in the positive y direction. And then I've got this uniformly distributed load. Now, when I want to use that as a load, I can use a resultant force. The magnitude of the resultant force is always the area of the shape. So if I draw out my UDL, right, I've got 10 on 6, and my resultant force for that is the area. So in this case, it is minus, because it's going in the opposite direction, 10 times 6. That gives me the area of the rectangle of the UDL, and that equals 0. So I can see that AY plus BY equals 60. Now, let's also note that this is the force, because this is 10 kilonewton per meter. This is 6 meter. So when I multiply kilonewton per meter times meter, I end up with kilonewton, with force. And now the last thing that I need to do is sum of moments. So sum of moments, in this case, I'm going to do them around A, with this being my positive direction for moment, so counterclockwise. Let's start off with the reactions at B. So Bx passes through point A, so it can't contribute a moment. Remember that to get a moment, you need force, but you also need a perpendicular distance. Here, there's no force because Bx is 0, but there is also no distance. So no moment from Bx around A. How about By? By contributes a positive moment, so plus By, and the perpendicular distance, that is By is in y, so the distance we're looking for is in x, is 6. Why is that a positive moment? Let's just have a quick look to see how this acts around B. So if I was to continue the line of action of B, it goes in this direction, and then I need to get back to A. So imagine you're driving your car, it's in the direction of By. Now I need to U-turn to get back to A, and you can see it is creating this moment. This moment is positive. Counterclockwise in my sign convention is positive. So plus By times 6. What about the UDL? So first thing, we can acknowledge that it is giving a negative moment. So minus. Moment is always force times distance. The force is the area. Okay, so that gives me the force. So 10 kilonewton per meter times 6 meters. Okay, that is the force, okay, area. Now I need to multiply that by the distance. And the distance is always the distance from the centroid of the shape to where we need to be. In this case, we're going here, right? This is the distance we need from the centroid of the shape to A. So that distance in our case, if all of this length is 6, this distance is half of 6, because the centroid of a rectangle is always in the middle. So that is going to be 6 divided by 2. So times 6 divided by 2, and that is the distance. And this, of course, is in meters. So I can see here that from here I got kilonewtons, and from here I got meters, and that gives me kilonewton meters, which are the right units for a moment. And that obviously has to be in equilibrium, so that needs to equal 0. So let's see what we've got. We've got 6 Vy equals, that's 3 times 10, so equals 30 times 6. I can divide by 6, so I end up here with Vy equals 30 kilonewtons. And now what I need to do is go back to this equation to find Ay. So Ay equals 60 minus Vy. That's just me rearranging that equation. And that is 60 minus 30. And so Ay equals 30 kilonewtons. So now what I want to do is I want to replace these reaction forces with the values. And so here I've got 30 kilonewtons and here I've got 30 kilonewtons. And let's do a little sense check. These are reaction forces, so they need to be in kilonewtons. That's what we got. Also, I can see that this beam is symmetric, so those two reaction forces need to equal each other. And that is what I got here, 30 and 30. So that all looks exactly as I'm expecting. So in this tutorial, we had a simply supported beam with a uniformly distributed load. The main things to take from here is to be mindful that when we're looking for the equivalent force of the UDL, or the uniformly distributed load, we are looking for the area of the shape that the distributed load gives us. When we're looking for distances to calculate the moment, we need the distance from the centroid of that shape that we just calculated to whatever point we're looking to find moments around. So I hope this all made sense, and join me for some more complicated cases as we continue to solve reactions and structural analysis. Bye for now.